Welcome! In this lecture, we are going to look at the dew point temperature and its relationship with cooling and dehumidification. Additionally, we will say a few words about the density of humid air. By definition, the dew point is the temperature at which the water vapor contained in the air will start to condensate when the air is cooled down. It is therefore a point located on the saturation line. Let's start again with this point, our example in the middle of the diagram. The temperature of the air is 24 degrees Celsius, the humidity is 9.5 gram per kilogram, corresponding to a partial water vapor pressure of 1.5 kilopascal. What happens when air cools down? Well, the temperature goes down, so the state on the diagram will go towards lower temperatures this way, or this way, or this one. Which one is right? Well, in physics and chemistry, there is an important law of conservation, and that's the conservation of mass. Mass cannot just disappear. So if we look at 1 kilogram of dry air and 9.5 gram of absolute humidity, this 9.5 gram of water vapor cannot just disappear. They remain there. Therefore, the left arrow is physically impossible as water vapor would just disappear. My arrow ends up here at 4 gram per kilogram. On the same way, the arrow right is physically impossible. Water vapor would just appear spontaneously, so cooling can only happen following a line of constant absolute humidity. What we call the dew point temperature is the temperature corresponding to the intersection of the line of constant absolute humidity with the saturation line, here therefore. It is the point at which water vapor starts to condensate, meaning that liquid water appears. In our case, it corresponds to a temperature of Td is 13 degrees Celsius. Please also note that all points on the line of constant absolute humidity do have the same dew point temperature, whatever the original temperature was. Maybe you ask yourself now what happens if you continue cooling after the dew point has been reached. Well, at dew point temperature, water droplets start to appear, just like here on the cold window. If you continue to cool down, more and more water vapor will condensate. This water vapor therefore leaves the air to end up as droplets water. The humid air contains therefore less and less water vapor. It is dehumidified, meaning it is drier. In my example, I stopped the cooling at 3 degrees Celsius, corresponding to an absolute humidity of 5 gram per kilogram. That is 4.5 gram less than originally. That is the principle on which dehumidification is based. That's also the reason why there is always a water drain in chillers. The condensed water must be drained away if the temperature goes below the dew point temperature. How do these processes look like in the psychrometric chart? Let's take the same point as before in the middle of the diagram. The temperature of the air is 24 degrees, the humidity is 9.5 gram per kilogram. To find the dew point, we need to cool the air going to the left, therefore, until the saturation line and following the line of constant absolute humidity, which is horizontal. As you see, the corresponding dew point temperature Td is 13 degrees Celsius. If we continue to cool the humid air, water vapor will condensate along the saturation line, leading to drier air. If the air is cooled until 3 degrees, the corresponding absolute humidity is 5 gram per kilogram dry air. It is useful to have an equation for more precise calculations or for pressures different from the atmospheric one at sea level. To derive this equation, you have first to realize that at dew point temperature, 13 degrees in our case, the saturated vapor pressure PWS is equal to PW, the partial pressure at our point at 24 degrees and 9.5 gram per kilogram absolute humidity. We have derived in another lecture that the saturated vapor pressure at a certain temperature T is given by this equation. We also derived that the partial pressure of water vapor Pw equals the total pressure times 0.00161 x. As we have just said, the dew point corresponds to the point where Pw equals Pws, Pws being the saturation pressure at Td. By combining both above equations, we can therefore write this. Working it out this way leads to the final equation, giving us the dew point temperature Td corresponding to any point of absolute humidity x. Be aware that in all equations on this slide, T is in degrees Celsius, X is in gram per kilogram dry air, and P is in kilopascal. So at atmospheric pressure, P is 101 kilopascal and not 1. Just make a check. If you fill in X is 9.5 and P is 101, you get Td is 17.6 times log of 2.099, which is 17.6 times 0.742, ending up to 13.06. Rounded is this 13 degrees Celsius. The density of humid air is shown by the dotted line starting from the y-axis. First, if we look at dry air, the line with zero absolute humidity, you can see that the density of dry air changes from a bit more than 1.36 below to a bit less than 1.14 above, so the axis goes from high to low. At 21 degrees Celsius, you recognize the density ρ of 1.2 that we mostly use when making ventilation calculations on dry air, like you can learn in the course Energy Demand. You can also observe that at constant temperature, the density of air decreases when the water content increases. So dry air is denser than humid air. For example, if we look at the temperature of 24 degrees, air with an absolute humidity of 2 grams per kilogram has a density of almost 1.19, while at an absolute humidity of 12 grams per kilogram, the density is 1.18. If you want to estimate the density of humid air, you can use this equation, which is derived from the ideal gas law. Here too, pay attention to the units in the equation. So, in this lecture, you have learned about the dew point temperature, which is the temperature at which water vapor in the air starts to condensate when the air is cooled down. You have also seen that dehumidification takes place when air is cooled further down. We also derived the equation used to calculate the dew point temperature, and you saw an equation to calculate the density of humid air. Humid air is less dense than dry air. Thank you for your attention.